So to start off with, we have to make sure that we are careful with our digits. Has everyone clicked in now? Including you, Claudia? 16. That's a really, really bad number. There is one, but I don't use it. Because in order to do that, you have to use a really crappy version of the teacher software, and it just ends up not being worth it. Sorry. So, if you want to click in, does anyone else need a clicker to borrow a clicker for today? I just happen to have a whole bunch of clickers. You have to enter this number. Don't erase the number that's on your current. Enter it for your current clicker. You have to have both of them registered, okay? All right. Closing that. Oh. So, most of you guys are wrong. So why is B the right answer? How do we count sig figs, Shane? How do we count sig figs for logarithmic values? Great, so this number here at the ones place or the tens place, that is 10 to the negative that. So let's talk about this for a minute. So whenever you see P in front of a letter or in front of a number, it means we take the negative log of that thing that's next to it. So if we have PH, that means we take the negative log of H, and it's really a bit lazy. It should be pH plus, right? So pH is negative log of the concentration of H plus. POH, negative log of the concentration of OH minus. So that P tells us that we're undergoing a logarithmic operation. And when we do that, the numbers, this is a question just answered, so ignore the 45 seconds. Sorry, I changed it up to be the title slide. The ones place tells us what order of magnitude it is. 10 to the negative third, 10 to the negative sixth. And then the numbers that are past the decimal are the ones that tell us, well, how accurate is that value? So let's take a look at these three examples that we have here. So if you look at these three examples, if I know that the pH, a logarithmic representation of concentration, is 4.31, how do I find the concentration of H plus in that solution? Write it down on your paper. How do you find the concentration of H plus at that pH value? And as you're doing that, think about sig figs. What's going on today? Why are so many people late? You guys know that I start right on time. Come on, guys, help me out. So who's written down how we find the concentration? Anyone want to write it out? You wrote it out? Sorry. Great, thank you. Okay, oh.
Not like that.
Sweet. Survived. All right, so Brian, tell us what you did. So 10 to the negative pH is a way of undoing that logarithmic value that we found. So a pH of 4.3 tells us the concentration of H plus ions. And I would add one little thing here. It's molarity. So then why is that ones place of the pH value not significant? Let's actually calculate that out. So if we do 10 to the negative pH, it's 4.9 times 10 to the negative fifth. So why was that 4 in the initial pH not significant? What did that 4 tell us? Let's write it out in decimal form too, maybe. What does that 4 tell us? Yeah, I'm talking about the 4 over here, this 4. Kind of. So it tells us something about the tens, where the decimal is, really. So this tells us we're about equal to 10 to the negative fourth. It's like looking over here, and this value is about 10 to the negative fourth. Well, it's a little bit bigger, a little bit smaller, because it's not exactly a pH of 4. But if we had a pH of 4, so pH 4.00 would be 1 times 10 to the negative fourth. That should be 1.00, right? So that 4 tells us where is the decimal. If we look at this number here, is that negative fifth significant? When we're counting sig figs for this concentration of H+, is that 5 significant that I'm pointing at right now? Do we use those to count sig figs? No. So what this pH is telling us is that we're close to 10 to the negative fourth concentration, but it's a little bit higher or lower. Whenever you guys look at a pH, a pKa, or a pOH, a P anything, you should be able to tell me with certainty, I know the decimal is about 10 to the negative m. In this case, you would say it's close to 10 to the negative fourth, but it's a little bit closer to 10 to the negative fifth than 10 to the negative fourth. So it's somewhere in between 10 to the negative fourth and fifth, because this is between a pH of 4 and 5. Let's look at the next example. So if we have a pKa of 10 to the negative, of 6.830, then what is this 6 telling us? Justin, what does this 6 tell us for pKa?
That the Ka is a little over 6.
So it's somewhere between a Ka of 10 to the negative 6 and 10 to the negative 7, right? Because this is getting close to 10 to the negative 7. And so if we do 10 to the negative pKa, if we calculate that value, it's 1.4 times 10 to the negative 7. So it's between 10 to the negative 6, 10 to the negative 7. So this is what the left of the decimal tells us, is what this negative exponent is going to be. That's why that number is not counted as any significant digits. But then we said, well, if I measure the pH and I measure 3 past the decimal, that means I have 3 sig figs. So that means that my Ka has to be 1.48. That 1.48, those 3 significant figures in non-logarithmic form come from the number past the decimal here. And then the exponent comes from where we are with the ones place. What questions do you guys have on that? Pauline? So A is, this is telling us what exponent, where the decimal is, and then these are telling us about the significance of that value.
Okay.
Same thing here. 6 tells us we're between Ka of negative 6 and negative 7, and then these 3 numbers here tell us where we are in between those two, and those 3 are significant. And so if we were to write that out, basically we're saying that the 10 to the negative 6 or 10 to the negative 7, that tells us how many zeros are here. That tells us how many placeholders we have. That doesn't give us significant information. The significance is how many values, how many digits are here. So there's 3 sets of rules now for sig figs. If you add or subtract, there's 1 set. If you divide or multiply, there's another set of rules. And the third one is with logarithms. Logarithms, once you can get comfortable with it, it's really easy. It doesn't change whenever you look at things. Just know, if we're showing a number that's a logarithmic value of something else, the number past the decimal. And then for the last one, how many sig figs is POH here? Kira, how many sig figs do we have?
I think it's either 3 or 4.
Which one is it on?
Neither of those. I want to say 3 based on everything I know about sig figs, but based on what you just said, I think it's 4.
It's 4. So the number past the decimal. 10 to the negative 0, that tells us where the decimal is. There's not much information there.
So why isn't that to the 0?
So it's between, this number is between 0 and 1. Do you agree? So if we just had a pH of 0, it's 10 to the negative 0. But it's between 10 negative 0 and 10 negative 1. So if you punch it in your calculator, you get this number, which is represented like this. So what I'm asking you guys to do is you should not need a calculator to tell me what 2 concentration orders of magnitude is between. When we see a pKa of 6 point something, you should be able to say, well, the Ka is between 10 to the negative 6 and 10 to the negative 7. Does that seem like a reasonable request? And then you can use a calculator to figure out the actual number over here, but you should be able to tell how many sig figs there are from what the pH is given. So a pH of 7, how many sig figs are there if we say pH 7?
0.
There are no significant digits, so people make that mistake all the time. And so I might even make that mistake. You guys might make that mistake. We'll try to catch each other if we do something silly like that. Why? Because 7 is the ones place. Chase?
No, I had a question.
Okay. So if 7 is the ones place, then that tells us it's 10 to the negative 7. But it doesn't tell us any significant digits. 7.0, that's 1 sig fig. 7.00, that's 2 sig figs.
If we had like a question and they give you a pH of 7, does that mean there's 6 sig figs, so your answer you couldn't write one?
Correct. You should not be able to write an answer if you have a pH of 7.
Okay.
So hopefully I don't make that mistake on an exam. No, it just has to do with we're not reporting any significant digits.
Most of the time when you see, oh, sorry, go ahead.
Would 7 point count as 1?
7 point would count as 0.
Okay.
Don?
Most of the time when you see pH, it's one digit. I mean, okay, this is 5.
Yeah.
I've never seen it.
Okay, guys, let's bring it back together. So this becomes important because we are going to say if someone measured a value, they're going to hopefully give us the appropriate number of sig figs, and based on that, we're going to determine what the concentration of things are. So it may not have been important when you're talking about a stream being a pH of 7 or 8, but now we're actually determining the exact ion concentration within that. So you guys are going to need to be a lot more specific. Is that fair? So we're upping in another level of precision. So my goal for you guys today is to be able to determine the pH of a weak solution of acid, or to go from pH to finding the concentration of the acid in solution. And then we're going to be doing that with a lot of ice tables. So we're going to be calculating the concentration of H+ using the ice tables and going back and forth in both directions. And from that, we're going to be discussing Ka and Kb, which is what your guys' workshop is going to be on tomorrow. So this is the question that we ended class saying that we would get into this. I think we calculated the last one before this, right? So we calculated when you had methane and hydrogen disulfide. This was on the worksheet from last class, but I want you guys to try to figure out what the concentration of H+ is if we start with a solution of HF, hydrofluoric acid, really nasty stuff. We have a 0.5 molar solution of that. Go ahead and take a minute, talk to your neighbors, try to figure out how we'd answer this. What information we might need, what information you can look up, how we answer this. All right, I hear a lot of side conversations going on.
It's because I don't know what I'm doing.
So, who has an idea? How would we start this problem? Taylor? Miata? Can we bring everybody back together, please? Brianna, can you share your thoughts?
pH is the log of the concentration of the solution, or of the acid in this case. You would just do negative log of 0.50.
Why is this totally wrong? Cosme? Okay, so we generate both hydrogen and fluoride when it separates, but that's not exactly the point we're getting at. Shane? If this is assumed to all generate that, what kind of an acid would that be? What kinds of acids completely dissociate? 100%. Is that a strong acid? If you guys don't remember your strong acids, figure that out immediately. No is the answer. That is not a strong acid. HCl, HBr, HI, nitric acid, sulfuric. There's a whole bunch of other acids. That is not one of them. So then what does that tell us? It's an acid. It generates H+, but how much? How do we describe how much product is produced in these types of reactions?
1 to 1.
Well, if it goes from left to right, 100%, then it would be 1 to 1. So wouldn't it be nice to have an equilibrium constant for this reaction? Wouldn't it be nice if someone had that number already figured out at room temperature of how much of HF actually splits apart and how much is on the together side? What would we call that? An equilibrium constant, and specifically for an acid, what's the equilibrium constant called? What's that? Ka. Look it up. Look up Ka for HF, and then use that to answer this question. What did you find? So it might be it. So use whichever one you want. All right, so did you guys find something like 7.1 times 10 negative 4th? What'd you find? 7.6? So if you look for, do you all look at the same temperature?
I didn't put temperature.
Okay, so for this problem going forward, let's use 7.1 times 10 to the negative 4th. What does that tell us? What's the first thing we know once we see that Ka? It's written up on the board. 7.1 times 10 negative 4th is a Ka we're going to use. And you can look up more accurate numbers. Sabrina, what do we know as soon as we see that Ka? What does that tell us? What's that?
Does it mean that our pH will fall somewhere in between 3 and 4?
It means the pKa will be somewhere between 3 and 4.
Does it mean that this reaction favors reactants is more to the left?
So it's a K, guys. What Taylor's saying is she's looking at it and she's saying, well, a K would be concentration of products over reactants. This number is less than 1, so that means it's going to favor reactants over products. Does everybody see where she did that from? Write out your K expression for this reaction. And then compare this number and see what you're going to have more of when all of the Kf dissociates, is going to, and that equilibrium is reached. So write out your expression of Ka. Write out your equilibrium constant. We've already done that. What's there going to be more of it at equilibrium? Reactants or products? Talk, figure it out. So Hannah, what are we going to have more of at equilibrium? Are products or reactants? Why reactants? Because what? Okay, so if we write out our Ka, I have it in the top right corner here. That number is less than 1. It's actually 7.1 times 10 to the 4th on the bottom and 1 on the top. That's what that negative 4 means. So that means we have a lot more of our reactant of the acid together than we have over here. So that is why HF is not a strong acid. If HF was a strong acid, what would Ka be? If it's a strong acid, it means everything's on the product side, 95% or more, which means that our K would have a very large number on top and a very small number on bottom. So that means we have a really big number for K. Okay, so now we know what Ka is. We know what it represents. So then how do we find the concentration of H plus ions once this reaction reaches equilibrium? Let's make a rice table. All right, so go ahead. Start with the concentration you know of each. Maybe let's do this one together. What's our initial concentration of HF? 0.50 molar. What's our initial concentration of H plus and F minus? We're going to assume those are 0 to start with. And then we need to say, well, what direction is the reaction going to go? Think about how we've done that in the past and figure out how to complete this table. Take about 2 or 3 minutes to complete this table. Raise your hand if you have any questions on how to start moving forward.
Every single week. Mommy tries getting me. Sometimes
This doesn't work so well in this big when everyone's looking down. So let's talk about this, guys. How do we figure out what direction this reaction is likely to go? once we pull our head out of all of our calculations and we just look at this, Salma?
If you compare Q to K and if Q is less than K, then it's going to favor the right.
Okay, so mathematically I completely agree. We find Q and we compare that to K. If we're going to draw a Gibbs free energy diagram for this reaction, here's all HF, here's H plus and F minus. Where is our minimum? Pretty far over this way, right? But then the question really is not what we're going to have at equilibrium, but where are we currently compared to equilibrium? So where in this graph are we now? Pat? We have no products at all. What would be another way to get to saying that our reaction is going to proceed to the right to reach equilibrium? How else could we look at this information and determine that the reaction will go to the right? Don?
Because you have if you have no products, it has to go that way.
So I 90% agree with you.
Not necessarily.
If we have no products and the K is not 0, then the reaction must go towards products. So just using common sense, well, there's nothing over here, so I think we're going to form something there. That's a totally legit way of describing this.
So anytime the Ka is under 1, wouldn't that mean that it's going to move towards the right?
So move is very deceptive. We're not comparing K to anything. We're comparing Q to K. So the question is, where are we, and how is it going to change to get to equilibrium? So K is this minimum down here. If we know what K is, that tells us when everything gets completely stable, we're going to have mostly reactions, but not all. And so then the question is, well, where are we now, and where will it change in order to get to the most stable mixture? Do you see the difference between those? So if I just say K is greater than 1, so we're going to be generating products. Now it doesn't tell us what we're going to generate. We need to know what we currently have in order to say where we're going to go to. So then what is our sign? What are we going to put under HF? What are we going to put as a change of HF? McKenna? You guys all agree, plus X. Okay, why is it minus X, Cosmo?
Because it's going to lower down.
That we have only that. So as the reaction goes forward, that's going to get used up. And it's going to break apart, and we're going to make some HF and F minus. How much HF and how much F minus are we going to make compared to the HF that's breaking apart, Val? So for every HF that breaks apart, how many H pluses and F minuses are we going to make? So we have plus X, plus X. The change in concentration is every HF that breaks apart and goes away, we generate one H plus and one F minus. This is really important to look back at our stoichiometric ratio for our equation. Questions so far? So then, what's our equilibrium concentration for HF? Tatiana? Based on this, what's our equilibrium concentration for HF? Why is everyone throwing away the sig figs? 0.50 molar minus X. Please don't get rid of that 0. I hate taking off points on the exam, or making Justin take off points on the exam, because you guys throw away your significant digits. If you keep it at every step, then it'll help you in the very end to know what you started with. What's our concentration of hydronium ions at equilibrium, Kirk?
0 plus X.
So X. And F minus, we really don't care about, but it also would be X.
I'm super confused now because it looks like at the table that H and F plus and minus are both X. So you said it wasn't a 1-to-1 ratio.
I said it's not a 1-to-1 ratio between the amount of HF we start with and the amount of H plus we generate. Maybe I misheard what you said. But if it's a strong acid, all of the HF generates H plus, and however many we start with is however many we end with. And maybe that's not what you were saying. Okay. Sorry, I missed out then. So I missed what you're saying. So you're completely right. If one HF breaks apart, it will generate one H plus and one F minus. So we good on that? So you were saying something that was right. I misunderstood. So now how do we find, if we find X, we find the concentration. We're good, right? So how do we find X? Megan? Okay, what's your question?
How come it's not 0.5 minus 2x?
So think about it this way. If this is one HF molecule, and it separates into an H and an F minus, how many of each of these did I make? And I started with?
But don't you take the same amounts for each one?
I take one molecule, it's composed of multiple things, and when that one molecule breaks apart, it generates one H plus, and it leaves behind the conjugate base.
So they're like half of an x?
It's not half of an X, because it's a number of things. It's like if I have 6 bicycles, am I going to get 6 times 2 wheels? Or am I going to get 6 wheels? So it's about that stoichiometric ratio. It's about every one thing that we take apart. And the same thing goes for any stuff we talk about. HF is a conglomerate of things. So if we have HF, and we say it's going to fall apart, it's going to break apart, and those two things we have afterwards, we're contained within that one original one. We don't have twice as many of them. So we can talk a little bit more later on. Hopefully as we go through this, it's going to be a little more clear. Salma?
To get X, don't we just do X?
Why would we do that?
Because you're just thinking about
Okay, so I'm going to extrapolate what you said. We already said that Ka is equal to the concentration at equilibrium, right up here in the corner, of H plus times F minus, divided by the concentration of HF at equilibrium. So that's X is our concentration of H plus, X is our concentration of F minus, and HF is 0.50 molar minus X. Everybody see how we did that? And then what's really nice here is that we know the numeric value of that, 7.1 times 10 to the negative 4th. So can you guys solve for X? How would we solve for X? It's going to be a what?
It's going to end up being x squared, so it'll make up for it.
Well, yes and no. So there's some really complicated things, and when we get into solubility, there's going to be 2x squared and some other things. So we need to make really sure that those x's are proportional to the stoichiometric ratio. So what do we need to do to find x now? Everyone want to do the quadratic?
No.
So how about we don't? How do we avoid doing the quadratic? Has anyone figured that out yet? Salma? Still going to give us a quadratic. I hate doing the quadratic. I really don't want to do it. So what do we do to avoid it?
When I did it on the pre-class or homework, whatever it was, I multiplied by the reciprocal on both sides. Like,
Yeah.
I did just normal algebra.
But then you got the quadratic, right?
No.
You should have got ax squared plus bx plus c.
No.
Yeah.
It said I was right, but I got my answer.
Okay. So here's this. If you don't get the next thing I say, then the rest of the semester will just be plugging crap into your calculator. How much of the reactants split into products? How much of that reaction actually generates products? Is it a lot, a little? Why do we say it's a little bit? How do we know that? Because our Ka tells us, not only is it favor reactants, but it's like 70,000 to 1. You guys see that? 1 over 70,000. Granted, it's not quite that, but it's about that order of magnitude. How big is that x, do you think? How much of this do you think is dissociating? How big do you think that x is compared to how much we started with? It's a really small amount. How big is this x compared to nothing? Okay, so this matters. This matters. But this x, we're going to do a little shortcut. And we're going to say, well, if that's less than 5% of the total, it's a logarithmic scale we're talking about in the end anyway. So I'm going to ignore that for a minute. How's that sound? So can we ignore this x? No, that's what we're trying to solve for. Let's not ignore x, okay? I have a lot of students, the first time I taught this, they're like, oh great, we just ignore x. Like, what? Then you don't, why do you do it? So we're saying, relative to the initial concentration, a really small amount of it is going to separate. So let's just kind of say, well, this is pretty much still 0.50 molar. So do that and then figure out what your H+ ion concentration is. True? You gotta check it out.
So maybe because I'm bad at math, I was already ignoring some of the work, that's why I got it.
Yeah, that could be.
I did not get about 0.50, I got about 0.01. So I thought I was going.
No, that's your x. I'm saying that 0.50 minus x is about 0.5. Yep, I'm not putting it up there yet. Calm down. Think about what it is. It can be a lot of different things. And I want you to describe all of those. Okay, so once you find that, try to answer the question that's at the top of this. Make sure that once you find x, you answer the question. Make sure you can articulate what x All right, everybody done? So question, what is x? So I wrote it up here, right? Ka is about equal to x squared over 0.50. We kind of are ignoring that minus x for now. What is this x that we're solving for? Chase, what is the x?
X is solving for, like, well, difference, like, how much the product is actually turning into.
Okay, so it's the change in concentration. Salma, what else is it? Okay, so that's one of the things that it describes. What else does it describe?
Is it the pH, like the amount of hydrogen?
So it's not the pH. It's something that we use to find the pH.
Number of protons.
Is it the, I don't know.
Thomas? Right? We said, what is the concentration of H plus at equilibrium? We said that is X. We just found X. So we need to go back to the table, and we can say X is a whole bunch of different things. X is the amount of our initial acid that dissociated, the minus X. X is the change in concentration of H plus, the change in concentration of F minus. X is also the concentration of H plus ions at equilibrium and the concentration of ions, F minus ions at equilibrium. Which one of those is important to answer this question? Kristen, which one do we use to answer this question? So we use that part in the bottom left? Why? To find the pH of the solution, how does that help us?
Because the left initial is going to be subtracted by like what is lost, so you have the final.
Okay, so we could find the final exactly by doing that, because we assume that there was no change, so there's probably a little bit of change. But that doesn't necessarily help us find the pH. So how do we find the pH now? Val? So if we find X through a number of steps, then the question, though, is asking about the constant. Oh, it was asking the concentration of.
Where is he going with this?
The next question on your worksheet. Okay. So you guys found the concentration of H plus. 0.19 molar. Good job, 3 of you guys. You ever feel like you have one of those days? Okay, so we had like 20-some people click in. Okay, so I think most of you guys found 0.0188 molar, right? How many sig figs should it be? 2 sig figs, 0.019 molar. And then the question is, was that reasonable? Could we make that approximation? Why do you say yes, Val?
So you have a quadratic and then calculate percent error and it was less than 2%.
So the error is not actually what we're looking about is for 2%. I mean, it's close, that's good. So I like the quantitative reasoning there. The way that we see whether that assumption was okay to make or not is, was there less than 5% of that initial acid? Is X less than 5% of what we started with? So basically saying, is the change from what we started with, is there 95% or more of what we started with still there? So what do you guys think? How do you figure out whether that assumption is valid, that approximation? Mathematically, how do we figure out if that assumption is valid? The ratio of what to what?
Of X to the initial concentration of HF.
Okay? So let's see if that is less than 5% of what we started with. In this case, the amount of X that went away was only 3.8% of what we started with. I need you guys to show this. Every time you make this assumption, this approximation, you have to validate it. Validating it just means taking X, dividing it by the initial concentration, and you can see, well, how much would that change have been? Or you could do the full quadratic, like Val did, but I want to see you doing the approximations as well, because that's a huge waste of time to do the quadratic.
Not be able to into your calculator automatically.
Even if you have it in your calculator. Michelle, you had a question?
So are we subtracting the X from the value, or I think
So let's do the next question then. The next question is, what is the pH of the solution? It's the same solution we've just been working with. I want you to click on the pHs. know, there's certain tables where you you always have to know what X is. All right, is everybody clicked in? All right, closing out.
I didn't get it on the last one. I had to make sure I got it.
Closing out.
It's fun to do though.
Oh, there's a lot of different numbers here.
It's the second one.
So,
Right.
how many sig figs should we have?
2.
So, what is 2 sig figs? 1.7 or 1.72?
1.72.
What is the number we just clicked in?
Oh, 7.
pH. pH is logarithmic. We use our log rules for how to find sig figs. So we need to have 2 past the decimal for 2 sig figs. So we had a concentration of H plus, which was also the concentration of F minus at equilibrium. Here's the trick, or the thing, it's not a trick, it's just what to keep in mind. As we're doing any ice table, anytime, if you forget what X is, you might as well not be doing it. So every time, just make sure you know what you're calculating, and then we can figure out how to use it. There's times where we're going to be looking at finding the concentration of OH minus. That is going to be our X. Do we take the negative log of concentration of OH minus to find pH? So we have to keep in mind what that value is we're calculating and how that relates to pH. Okay, so we just take the negative log of the concentration of H plus ions. We get 1.72 as our pH. So go ahead and click in now. And think about, we just did this exact problem. We now have a different initial concentration of HF. See if you can think of any shortcuts to do in order to find the pH of this solution. You might use your work you've already done. Oh, sorry, question number 2 on your worksheet, I messed up. It's not the right number for concentration, so it's on the screen. That's what.
You added an extra.
Oh, it's question number 3. It's question 3. It's question 3. No, this is 2 sig figs. pH is the logarithmic. So what do you look at? Can you look back here at your work and see what you can do similarly here? Now we have different initial concentrations of HF.
So we're just finding pH of this plugging and clicking it. Okay, I don't know. I thought this was asking us to like explain.
What is that? Where did you find that?
Mine's 0.05 in instead of 0.5.
Okay, so you x squared over 0.05 equals Ka.
Yeah.
And then you solve for x.
Yeah. But then that's what that was. But you
And that's x. So why are you doing that? Yep, so what that's all.
it's not valid.
Yay. Teamwork.
Question? What? Write out some stuff.
It's in my head.
Everything. Write out everything. No, All right, so how do we approach this? What's similar about this, Katie? No, just tell us about the process. I don't want the number.
You still like can plug in the new concentration, like the one for HF. So you put that in the bottom of like your KA.
Okay, so I'm going to summarize what you said. Our Ka is the same. Our Ka didn't change. It's the same acid. It's at the same temperature. So Ka is still valid. But then in the bottom, instead of writing out 0.50, we can write 0.050. And I think on your paper I had different sig figs than I have up here. Sorry about that. So then we just solve for x, right? And then we take the negative log of that and we find our pH. What is this little step I have here? So did anyone use a quadratic on this? What is the step I have written up there right now, guys? What is this? Tatiana?
To check and see if the assumption that 0.050 minus x is the same thing, possibly the same thing as 0.05, if it's valid.
And what did we find?
It's not.
It's not valid. So we had to check our approximation. The approximation was not valid. So even though we know we have a small Ka, there's certain times where you check the approximation and it's not valid. And then, how do we solve for x? Either the quadratic or, what's that?
Make another estimation and change your number.
It's called the rule of successive approximations, where you plug in what you find for x back in, plug it, and then find the new x, plug it back in, find the new x, plug it back in, and you get closer to the value. Oh, don't worry about it. Don't do it. So what I'm getting at here is that it's not quite as straightforward as just looking at Ka. I can pretty much tell you that unless I make a mistake on an exam, I would never have you guys do the quadratic because I don't assume that everyone has in their calculator, and I don't think it's worth the time you put in. Is that fair? But on your homework, there might be some quadratics. You have to check your assumption to determine whether you can ignore that x or not. That change in initial concentration.
I have a question for when we inevitably have to do that. What is A and what is B and what is C?
So it's ax squared plus bx plus c. So when you take any equation and you set it equal to 0, you have ax squared plus bx plus c. So you'll have some amount of x squared, some amount of x's, and some just extra numbers left over, and that's what you plug in for A, B, and C. So we can chat after class about it if you want, but there's certain values that we'll just find and we'll use those. So let's take a look at this graph here. And I want you guys to try to infer some information from what you see on this graph about percent ionization related to concentration.
You're saying as the concentration of the reactants decreases?
So it's the
Or are we no longer talking about the HF thing?
any acid. So as the concentration of our acid decreases, what happens to percent ionization? Closing out. Kirk, you have a question on this? Okay, so let's answer this and let's go back to the previous question in 1 second. Tatiana, can I get you back square and center? So can someone describe what they see when they look at this graph? What happens, how do we read this to determine what happens to percent ionization as concentration changes? Solomon?
The concentration goes to the left, so the percent ionization increases.
Did we just find that too? When we had 0.5 molar, the assumption was valid. There wasn't that much ionizing. As you get more and more dilute, less and less concentrated, the amount that separates increases. And that all has to do with probability of how many molecules are around, what they're likely to run into. We're not going to get into that too much. But if we have very dilute solutions, then we have to be more careful about this. Or if we have stronger acids, we have to be more careful about this. Kirk, what was your question?
For the last question that we did with the changing the concentration, so was our answer to this question that we can't solve it because we can't validate?
We can solve it, but we have to use a quadratic to solve it, and I don't want to do that.
Okay, that's.
So you guys would have to do that. I'm not going to do it. Just kidding. No, so just really to bring out the point that in a more dilute solution, we would have to use a quadratic in order to find the pH.
Okay.
One thing we could say for sure is the pH is going to be higher than it was for a 0.5 molar HF solution, but unless you do the quadratic, you can't tell exactly how much higher. All right. So what do we call this specific equilibrium constant for the reaction above? All right, so we have our Ka, specific for an acid reaction. What reaction is happening to this acid? Is this an acid-base reaction? So circle what acid we have, and circle the base we have.
The base is water, right?
So the way that this reaction is written out right now, we have water as our base. H plus ions, I hope when you guys, when we did the colligative properties, you're thinking about things that are dissolved. That there's stuff that's floating around within water, water helps solvate it. But those things don't just sit there by themselves, they actually are associated with water molecules that are around. And H plus ions don't actually just sit around, they actually form hydronium. One of the lone pairs in water will actually bond to the H plus and make H3O plus. Yeah? Water can act as both an acid and a base. So if we have water, it has two lone pairs. If there's an H plus floating around, that means it has no electrons. That means that one of the lone pairs of electrons can bond with the H plus, and that gives us hydronium. What am I missing from that Lewis structure? That's hydronium. Not super stable, but it exists. It's more stable than H plus floating around by itself and not associated with anything. Yeah?
I'm just trying to wrap my head around this. I've always been told that water is a weak acid.
Water is a
That
weak
was
base.
really weak acid. But
Water's
is
both.
it that if we see it in one of the
So let me do a second drawing.
these equations, if it's on the reaction side with a base, is it an acid, and if it's with an acid, it's
So let's get out of... So that the memorization helps us if we know water acts as an acid, right? Or it helps us know the water acts as a base. I want to show both. So let's draw water acting as an acid. What does that mean? Donate to hydrogen. So let's say that water comes in contact with ammonia, a weak base. That means that ammonia can steal a proton from water. What else is left over? Not quite. So water can act as an acid if it's in the presence of a base, or water can act as a base if it's in the presence of an acid. It does both. And whenever we think about writing out a Ka expression, especially for Kb, when we talk about how strong a base is, it's all about how likely is something to give a proton to water, that's Ka. How likely is something to take a proton from water, that's Kb. And we'll be doing some more examples of that throughout class. So, how does Ka that we wrote recently relate to this, to Kc? Maybe go ahead and write out Kc for the reaction that's written at the very top of the slide. I want everyone to write out Kc. I think there's space in your paper to write this out. then think about how we wrote out Ka for the previous reaction, how that's different. All right, I think about everyone's written it in there. So can someone read off what they have for Kc? Can I get Miata? What do you have written for Kc? Shavante, can you help out?
For the concentration of CH3COO times the concentration of H3O over the concentration of CH3COOH.
Almost. So one, I'd want you to add the charges when you talked about it. And I really like that you changed it to say concentration of, because that's really important. Not the number of moles. We can never use moles in K. So what were you missing? And why? So do we put water in this reaction or no?
I didn't think we did.
We do. So when do we and when do we not include water in our equilibrium constant? Solid? Okay, if it's a solid, it means it's not reacting. It means it can be in a bathtub of this stuff. That if it's not dissolved, it doesn't matter.
Is it that if it were a product, we wouldn't include it, but since it's reacting with the...
Not about what side of the reaction it's on.
Is it Kc versus Ka?
So Kc versus Ka is where they separate, where we have difference. Any other ideas, Taylor?
Is it because it's an acid-base reaction?
Because it's the base. It's reacting. That's a reactant. If the solvent reacts in the reaction, it has to be in there, because reactants, concentration of products over reactants, right? Kc explains any chemical reactions that occur. We just said the water is needed in order to pull that proton in order to make H3O+, right? H3O+ doesn't form without water being there. So that is called Kc. But we don't want to talk about the concentration of water. There's so much of it. So what we're going to do is we're going to simplify our lives, and we're going to talk about just the business end of this reaction. And so to do that, we kind of put a filter on, and we say, well, let's just look at what's changing. Since the concentration of water throughout this reaction is fairly constant, because it is surrounded by water as well as it being a reactant, then just like we talked about K prime in our reaction, if something is in that much excess, well, let's wrap it up into the constant. So why don't we multiply both sides by the concentration of water? That simplifies our right side. Everybody see what we're doing here? So if we multiply both sides by the concentration of water, then on the left side we have a new constant. The concentration of water times Kc. What do we call that constant? That's our Ka. So just like we did K prime in your kinetics lab, where we simplified the concentration of something that really wasn't changing at all, we wrapped that up into the constant. So we're doing the same thing here. So when you guys look up Ka, that is only the concentration of the conjugate base and H plus or H3O plus divided by the concentration of our weak acid. That's why on that last slide we had HF, the concentration of H plus times the concentration of F minus divided by HF concentration. We didn't have water in that expression. Taylor, you have a question on that?
Doesn't the aqueous mean that those ions are...
Yep, it means that not only is water a reactant, but it means that water is everywhere else as well.
So I was going to ask, why is it liquid and not aqueous if there's like ions floating around?
Ions of water?
Yeah, like the hydrogen ions. Like, say if you're saying well, it's a base, but wouldn't that mean that there's ions, like, the O is more than the H or something? So why are they like aqueous?
No, so we said before, so there's a weak base and there's a strong base. A strong base is OH minus, usually attached to a metal. A weak base is something with a nitrogen or an oxygen that has a lone pair that can pull an H plus towards it. So in this case, this example, water acts as a very weak base because it holds on to that proton. It accepts it. So we don't generate any OH minus in this reaction. So let's look at sodium bicarbonate. I want you to go ahead and write the expression, Ka expression for sodium bicarbonate. Think back to your Lewis structures.
Still using water, right?
These are all dissolved in water for the rest of the semester.
Oh, you want this plus water?
Not quite. So what happens when that compound goes into water? What do we have?
You had to have NaHCO3 to make the NA.
Which?
NaHCO3.
So that's a container. I can go get a jar from there. We bring it in, we put it into water. How do we write out?
Oh, so we're adding that, we're doing that plus water.
Yep.
So sorry.
Nope.
No.
On the right track. But think about what happens when we put this in water.
Okay.
All right, let's bring everyone back together.
Yeah.
What are you guys all forgetting about? When we look at this compound, what's the first thing that we should do besides focusing on an equilibrium? Is there anything that happens immediately without an equilibrium that goes to completion first? We have an ionic compound. When ionic compounds go into water, the ionic bonds separate. What is our product of that first dissolving step? So go ahead and write the total ionic reaction of the weak acid that you actually have, not the ionic compound, the weak acid after the ion dissociates with water.
So many bags. So many bags.
I know, I got too much.
How's it going, Justin? Great.
I'm giving them back.
Oh, really?
Yeah, that's why I came today.
What's up, buddy? No. No. All right, take about 30 more seconds. Try to write out this equation.
Isn't that like a product?
That's what you put into water. And then what separates when this goes into water.
Na plus.
Yes. And then NA
It's
plus.
CO3 2
The ionic bond separates, and then we have a weak acid.
Like, I mean,
Yeah. No, CO3 2 Yes. And then no, that's okay.
What happened to your oxygens?
If it was on the left.
There's one there and two there. One.
So you're not losing oxygen in this. All right, guys, who wants to talk through their total ionic equation? What did you do first? Pauline, the first thing we did was?
It's water
Okay? But if it's the total ionic equation, then we have to have all the things written out as ions. So we have Na plus and bicarbonate. And then that had water added to it. And then as water was added to that, what happened to our bicarbonate? Thomas? The bicarbonate, what happened to it? HCO3 minus. Say again? It dissociated to some extent. Water acted as the base. Water accepted a proton from bicarbonate and left carbonate ion. What's the total ionic equation then? Or the net, sorry, as I can talk. What's the net ionic equation for this? Brian? Are there any spectator ions? Can I simplify this to get a net ionic equation? What's that? Justin says Na+. We have a spectator ion. So when we rewrite this as the net ionic equation, that is our Ka. You guys are going to be working a lot with salts in the next 3-4 weeks. That means the first thing you have to do whenever you see a salt is let's separate the ionic bonds and see what we have in solution. And then we say, are any of those going to interact with water in order to release or accept a proton? So you guys got to get in the habit of doing these. And then the last thing, go ahead and write Ka. If you haven't already, go ahead and write your Ka expression, not Kc, write Ka. Sarah, can you read out what you have for your Ka expression? Can you please read it? Mommy, can you help?
Yeah, I have KC equals concentration of CO3 times concentration of H3O.
So I don't know why both of you are leaving out your charges. So either say the name of the polyatomic ion or say the full thing with the charge. Sounds like a little difference, but it's a really important difference. So say it one more time, that final part.
Oh, okay, so concentration of CO3 or 2 negative times concentration of H3O plus over HCO, the concentration of H3O.
Great, thanks. So the other way to say that would be the concentration of carbonate times the concentration of hydronium all over the concentration of bicarbonate. I like how you also said Kc times the concentration of water. So we're not going to use that necessarily, but the fact that you're recognizing that is great. And so for this particular reaction, is this a strong acid? How do we know it's not, Alex? Because there's a lot more reactants. The last one was 10 to the negative 4, and that was a weak acid. This is a super weak acid. So this reaction doesn't favor products very well at all. This actually acts as more of a base probably, but we'll be talking about that more next class. So I think you guys just answered this last clicker question. Last question. If we have a strong acid, the Ka value is likely to be 10 seconds. Do the same for the rest of the questions. What about for a weak acid? And then we'll start up class. After you guys vote on Tuesday, we don't have class, next Thursday. So a strong acid is going to have a Ka that is really big. Does anyone want their exams back?
No.
Justin, thank you for grading and bringing them back. You guys can all see Justin. He's going to hand back the exams today. I'll post the grades soon.